Now let us do some exercises on finding out shape functions using the isoparametric formulation. So let us start with this linear element which has a node 1 at a coordinate x1, then is L of L length in the physical space, and there's a third node at a distance L by 2 from node 1. So this should be mapped in the isoparametric formulation. This should be mapped from a parent which lies between -1 and 1. So in this parent element, node 1 will be at r equal to 1. R is the only coordinate. R is the only coordinate in the parent space. Node 2 will be, R will, this node 1 will be at r equal to -1. Node 2 will be at r equal to 1. And node 3 will be at r equal to 0. So these points will map to these physical points in the physical element. Now in this we can find the shape functions using Lagrange polynomials. N1 will be a function which is 1 at 1, 0 at 0, and then 0 at 1 again. So that function is this one. This is exactly that function. This you can verify is N2, and this is N3. Now if you write the coordinate mapping, x equal to x is at any point inside the element is n1 x1 plus n2 x2 plus n3 x3. x1 is x1, x2 is x1 plus L, and x3 is x1 plus L by 2. You plug that in, and then if you know the value of x1, you get the value of x at any point inside the element. Now in the Jacobian, all we need in the Jacobian is dx dr. This is a 1D element, so this is all that we need, and it's easy to verify from this mapping function that dx dr is going to be L by 2. Note that the Jacobian, the determinant of the Jacobian rather, so the determinant of the Jacobian is the Jacobian itself here. So the determinant of the Jacobian gives the ratio between the volume in the physical space to the volume in the parent space. In this case, the volume is the length. So in the parent space, the length is 2. In the physical space, the length is L, and therefore, as expected, J turns out to be L by 2, which is the ratio of the lengths. Now, J inverse obviously will be 2 by L, and determinant of J will also be L by 2. So, so only strain in a 1D truss element is epsilon xx, which is in this case du dx. So you write it as du dr times dr dx. Dx dr is J, so dr dx is J inverse, and therefore this would be 2 by L into du dr. And du dr, so du dr will be given by, u will be given again by n1 u1 plus n2 u2 plus n3 u3, which means that du dx, which is epsilon xx, will be given by dn1 dx dr u1 plus dn2 dr u2 plus dn3 dr u3, and this whole thing multiplied with dr times dx. So will give you dn1 dx, dn2 dx, and so on. Dr dx is 2 by L, and therefore this will be the expression for the B matrix. So this will be the expression for the B matrix. The B matrix would be dr dx times So this would be your V matrix, and this is what we have written here. So now let us take this case. So this is a 4-noded Q4 element, and this is, we know, is mapped from a parent which looks like this. This is R, this is S. And now if you remember, we had in our parent that we did, we had numbered the nodes as 1, 2, 3 and 4, uh, but we have also figured out that in the physical space, in the one-to-one mapping, 1 will map onto the node at the bottom left corner, 2 will map to the bottom right corner, 3 to the bottom right corner, top right corner, and 4 to the top left corner. So that's what is going to happen. And now the node numbering is different. It's still anti-clockwise, but this is 1. So this should map here. So I'll call this as 1, this is 2, this is 3, and this is 4, according to this numbering. Now, once I have done that, I will have to change the ordering of my shape functions. So what is 1 now, what is going to be n1 now, was my n3 in the beginning, in my was my n3 in my scheme of things that we did earlier. This was n3. What is 2 now was my n4, and so on. So I will now change the ordering. I'll now change the ordering. So doing that, I will write down the mapping from X, Y to RS, and this is going to be these are going to be my shape functions. These are going to be my shape functions. So this was my n3 earlier, but now it's my n1. Similarly, this was my n4, I think. Now it's n2, and so on. And the coordinates, this is x1, which is the coordinate of x coordinate of this point. So this point is at 1 comma 5 by 4, I think. This is at -1 comma 1 by 4. This is at -1 comma -3 by 4, and this is at +1 -3 by 4. So these are the coordinates, and that's what I will use here. So these are the coordinates that I have used. And then the Jacobian matrix would be del x del r del x del s del y del r del y del s. This would be Jacobian, and that is, if you carry out the derivatives, this is what you should get. Once you have got the Jacobian, you will have to get the strain displacement matrix. So the strain displacement matrix, we have talked about it before. This is the form of the strain displacement matrix. So in this case, you will I leave it to you to find out the strain displacement matrix on your own. Sorry, the Jacobian would be dx dr dy dr, then dx ds dy ds. This would be the Jacobian, and this Jacobian is calculated here. So from these two expressions, so you can find the determinant of this, which will be a function of R and S, and you can find the strain displacement matrix in the way that I discussed in the lectures. So the strain displacement matrix, remember, would connect epsilon xx, epsilon yy, and 2 epsilon xy with, so this is the strain displacement matrix, with u1, v1, u2, v2, u3, v3, Q4, V4. So this is the nodal displacement. This is the vector of nodal displacements, and you can use the interpolation to find this out. You will also need the J matrix and the J inverse matrix, which we have called gamma, and you can easily find B in the manner that was shown in the lecture. Now let's go to the third one, where we will now only find the shape functions and leave the rest to you. Now, to find the shape functions, what you need to see here is you have different levels of, so this will of course be mapped from a similar parent. So this, let's erase this parent, and so this parent now is again going to be one by one. This is RS. So 3 will map from here, 4 will map from here, and then I'll have 1 here. Halfway between 1 and the r equal to 0 line, I'll have 6. Halfway between -1 and the 0 line, we will have 5. We'll have 2 here, and 7 will lie on the s equal to 0 line. So this would be my parent, and this is again 1, this is 1, this is 1, so this is my parent. And right now, now what we see is, let us look at 2, 5, and 6. So in the r direction, there are 1, 2, 3, 4 nodes. So this would be a third order polynomial. Every one of 2, 5, and 6 would be third order polynomial in R, but in the S direction, they are linear because there are only 2 nodes. So it would be a combination of a third order polynomial in R and a linear polynomial in S, and the linear polynomial at s equal to -1 should go to 0. So remember, n2 should be 0 at node 3 and node 4. So so on so this is the linear part, and at s equal to -1, all these three go to 0. So n5, n6, and n2 would be given by these functions. These are third order polynomials, which are third order Lagrange polynomials that we have derived, which are which is, for example, 1 here, 0 here, 0 here, and 0 here. So this is the third order polynomial, Lagrange polynomial for n2. Similarly, for n5, the third order polynomial would be like this, and so on for n6. So these are third order polynomials in R, third order Lagrange polynomials in R, and first order Lagrange polynomials in S. Let us look at the other nodes now. So if you look at n3, you will see that n3 has to be bilinear. So n3 is linear in this direction. There are two nodes along this. So n3 would be bilinear. Take two Lagrange polynomials which are linear in R and linear in S, which has to be 1 here, 0 here, 1 here, 0 here, and then you get n3 to be this. n7 is quadratic in S and linear in R. So n7 would be 1 here, 0 here. So it will be in the S direction, it would be quadratic. But in the Y direction, it has to go to 0 on this boundary. So in the R direction, it has to be linear. It has to go to 0 at R equal to -1. At R equal to -1, it has to go to 0, and that is your n7. Similarly, n4 N4 is quadratic in S and linear in R, and you can show that N4 can be written like this in terms of N7. And finally, N1 is a combination of N1 is a combination of a quadratic curve, which is like this in S, and a cubic curve, which is like this in R. So the combination of these two will give you N1 for this case. So, and you can also show that N1 can be written in terms of N5, N6, N7 in this manner. So this is actually the linear bilinear approximation that we had done for the 4-noded Q4 element. And these are corrections. These are corrections that you will do for the presence of N5, N6, and N7 along uh, along the way. So these are terms that you need to add if N5 fifth node exists, sixth node exists, and seventh node exists, just like we had done in these tables here. So these are terms which are added if fifth node exists, if eighth node exists, and so on. And that's why we chose to write it in this manner as corrections due to N5, N6, N7. Of course, you can write it as a combination of cubic and quadratic curve in R and S. Okay, so this completes our small exercise on formulating shape functions. From here on, you can take over and form the Jacobian for this case, determinant of the Jacobian for this case, both of which would depend on R and S, and then go on to find the strain displacement matrix. Let us briefly look at triangles now. So triangles, this is a physical triangle. So you can have T3 elements like we have studied. You can also have T6 elements where nodes are added at the centers of the edges, at the midpoints of the edges. We will study only these two. You can have other kinds of triangles also, which are special purpose triangles, but T3 and T6 are the most useful ones. And it is customary to map the triangles from a parent that is a right angle triangle. Topologically similar, but it's a right angle triangle. So this is the mapping that we do. So what we envisage is these corner nodes will map from the corner nodes of the right angle triangle, and these mid-side nodes 4, 5, and 6 will also be located at the mid-sides of the right angled parent. Now this length is 1, this length is also 1, so the area of the triangle is half. Area of the parent triangle, area of the parent is equal to half. Now a little bit about the triangular coordinates that we use, we have already talked about. So the coordinates of a point can be given in terms of the areas of these three triangles that divide the main triangle into three parts. So this one is called A3, its opposite node 3. This one will be called A2, and this will be called A1. Now if you see, when this point lies on the line 1, 2, A3 is equal to 0. A3 is equal to 0. So in the three-noded triangle T3 case, we had defined N3 to be equal to A3 by the total area of the triangle, which in this case is half. N2 we had defined as A2 by delta, and N1 we had defined as A1 by delta. This would come in very handy here. So if you see, A3 is equal to 0 on this line. And let us define A3 by delta as S, as my mapped coordinate. Remember, it was R and S in case of quadrilaterals and rectangles. So N3, let us take it to be S. So this point lies on, when it's here, S is equal to 0. So this is a line on which S is equal to 0. When this point lies on the line 1, 3, A2 is equal to 0. Therefore, R is equal to 0. We have defined A2 by delta as R. So, R is equal to 0. So, this is my R equal to 0 line, and therefore, it's the S axis, and this is the R axis. When this point lies on node 2, then A3 is 0, but A2 is the whole triangle. A2 is the whole triangle, and therefore N2 is equal to 1 and R is also equal to 1. So this point can be treated as your 1, 0. This point similarly can be treated as your 0, 1. And this point can be treated as 0, 0, because then when R and S both are 0, N1 is equal to 1, as it should be at this point. So the definition in case of a three-noded T3 element is N1 equal to 1 minus R minus S, N2 is equal to R, and N3 equal to S. So this is the convention that this is the trick that is followed in case of triangular elements, parent triangular elements which are right angled. Now, this is where I will map my physical element in exactly the same way. And for T3, these would be my, my shape functions. Now, if I have a quadratic triangle, for example, I have nodes in between as well. So when I have that, then I will use these functions, these three functions. So zeta 1 is 1 minus R minus S, zeta 2 is R, zeta 3 is S, which are basically N1, N2, N3 for my T3 element, and I will enrich them. I will enrich N1, N2, N3 and add N4, N5, N6, which are for the mid-side nodes, to get the shape functions. And these would be the shape functions in terms of these functions, these three functions of R and S, and you can verify that they satisfy the Kronecker delta property for the 6-noded triangle. Now, there are a couple of formulas that apply to triangles and that are very useful when we later deal with them, when we write stiffness matrices, or we write we integrate quantities over the area of the triangle. These are the two formulas. I'm not going to read them out. So these are the two formulas which are very useful, and we will use them quite a bit when we deal with triangles. So that's all about triangles. We'll do a small problem, and this problem is like this. So I have a triangle which has a node 1 located at 0, 0, node 2 located at 4, 0, and node 3 at 1, 3. So somewhere here. So this is my physical element, and I will now write down the shape functions, strain displacement matrices, and so on. So my shape functions, this is 1, 2, 3. This ordering is the same as what I have chosen. So my shape functions, N1 will be 1 minus R minus S, N2 will be R, and N3 will be S, which means at the coordinates of any point will be given as 1 minus R minus S x1 plus R x2 plus S x3, 1 minus R minus X y1 plus R y2 plus S y3. And x1 is, this one is 0 for this element, this one is 0 for this element, this guy is 0 for this element, this is 4, and this is x3 is 1 and 3, this is 1 and this is 3. So y would be 3s and x would be 4r plus s. So you calculate del x, del r, that would be 4, del x, del s, that would be 1, del y, del r, that would be 0, and del y, del s, that would be 3. So this becomes your Jacobian. And uh, invert this Jacobian. If you invert this Jacobian, this is your J inverse, and you write the derivatives of any function del x del y in terms derivatives in the parent coordinate system through the J inverse. So this is what my um, inverse relation is. Determinant of J is also clear. Det J, which we call J, is equal to 12. So now the shape function matrix, remember the shape function matrix that we wrote was, so the shape function relates and so on with the u and v at any point inside the element. So the shape function matrix is like this. So it is 6 cross 2, and this would be your shape function matrix because we know these functions. The strain displacement matrix can be similarly calculated, and to calculate that you have to again calculate epsilon xx, epsilon yy, and 2 epsilon xy. You have to remember that this is del u del x, this is del v del y, and this is del u del y plus del v del x. And each of these del x, del y would be governed by the relation you have. So del x will be, this we call gamma generally. Del x would be gamma 1 del r plus gamma 1 2 del s. Del y would be gamma 2 1 del r plus gamma 2 2 del s. And you have to use those relations here to get the B matrix, which I'm sure you can do on your own.